we're going to talk about potential energy. So last time we talked about this, if I take a mass, or maybe two times ago, I don't remember. If I take an object with mass m and lift it a vertical distance delta y, how much work have I done on the object? mg delta y, right? And if I do work on the object, that means I put energy into the object in some form or another. But if I do this at constant speed, that means I'm not changing the object's kinetic energy. But what does change? The height, so the position of the object. And that's how you can think of potential energy. Potential energy is energy of position. I've changed the object's location with respect to the Earth's gravitational field. Yeah. So the work I did in the object then caused a change in potential energy. And conservative forces have potential energies associated with them. If I lift an object up, am I increasing or decreasing its potential energy? Increasing, right, because if I let it go, then when it gets back to that same spot, it'll have more energy than it did before. I'll just give you a formula. Potential energy for gravitation is mgy. So a change in gravitational potential energy is mg delta y, as long as we're staying near the surface of the Earth. As I said before, we'll do a unit on planetary orbits later in the year, and then we'll have to get something different that will correspond to the law of gravitation. And spring potential energy is 1/2 kx squared. Therefore, a change in spring potential energy is 1/2 k x final squared minus 1/2 k. Oops, that doesn't look like a k. X naught squared. Right. And, or depending on what's convenient, you could also factor that, 1/2 k times x final squared minus x naught squared. So if we've got a spring with constant k hanging from the ceiling at its relaxed position, why not? Mass m is attached to it, then released. When the system comes to rest, the mass is at position y final. What is its change in potential energy? Yeah, so what kind or kinds of potential energy are present here? Gravitational and?
Spring force.
Gravitational and spring potential energy. So our change in potential energy is our change in gravitational potential energy plus change in spring potential energy. Oh, I just kind of blew past this. We use U for potential energy. I don't really know why, but yeah, accept it. All right, what is my change in gravitational potential energy going to be? What final? What?
Y final.
What'd you say?
C final.
Right, exactly. And since y final is lower than y naught, this will wind up being negative. And then for spring, what do we have? Right. Don't just subtract them and square it. That would be wrong. Right. So we've got a change in potential energy. There's a change in gravitational potential energy. There's a change in spring potential energy. And gravitational, the change in gravitational potential will be negative. Change in spring potential will be positive. Yeah. All right. Now, only a change in potential energy actually matters because things happen when energy goes into a system or out of a system or changes form within the system. So as long as potential energy remains constant, then nothing of interest is happening in terms of energy. So because of this, we can set the zero of potential energy wherever we darn well please. For some problems, it'll be convenient. You can pick where you want the zero to be. So pick whatever makes the calculation the easiest. Sometimes it won't matter. But like, if you have an object that starts at one height and ends at another height, make one of those heights the zero. Don't make somewhere in the middle zero. That would be silly. Right? For gravitation, it is often convenient. What do you think would be a convenient place to put the zero? Initial height, sometimes, sure. What did you say?
Height, fine.
Final, yeah, initial or final height works. A lot of times it's measured relative to the ground or the floor. But you are correct in saying that initial or final height is probably the best place to set your zero. For a spring, we typically set the zero. Where would you guess? What's kind of the baseline point for a spring? Where do we measure the force from? Equilibrium is generally the most convenient place to set our zero for the spring. Not necessarily. It could be. But for a spring, it is easier to set it at equilibrium. Because that's the point where if you let go, nothing happens. So it makes sense to call that the point of zero energy. For a vertical spring, there's kind of a special thing that happens. So let's say we've got a vertical spring, and this vertical spring, if it is at equilibrium for the spring, it sits at this position. I'll call it YEQ for equilibrium. If we attach a mass to it, where's it going to go?
Down.
It's going to go down. Okay, I'll call this why not, because why not? And then let's say there's some other height where the mass is, and we'll call that Y final. Now, if a spring is vertical, you need to be careful about the language you see in the problem, because there are two different things that could be called equilibrium. Okay, the unstretched spring is at the spring's equilibrium length. However, there is also an equilibrium position for the mass spring system. So remember, equilibrium means net force is zero. So you've got equilibrium of the spring, which is where it's sitting when it's unstretched, and then there's an equilibrium position for the mass spring system, which is where the spring force equals the gravitational force, and therefore the mass is in equilibrium. Okay, does that make sense? So make sure you're reading the language of the problem if it gives you something, so you know if it's equilibrium for the spring or equilibrium for the mass spring system. Okay, so now I'm going to say that why not is the equilibrium position of the mass spring system. Now let us find the change in potential energy from Y naught to Y final. All right, so and we're going to say this is the zero, this equilibrium length of the spring, we're going to say that's the zero of potential energy. Right. So, what's my gravitational potential energy at Well, between these two places, what's my change in gravitational potential energy? mgy final minus y initial, sort of. But if we're calling our gravitational, if we're saying our zero potential energy is here, then we're actually this far below that. So at y final, we have gravitational potential energy mg times negative y final, right? So then, and the same thing for y naught, so it winds up switching. It's mg y, yeah, it's mg negative y final minus negative y naught. Does that make sense? Okay. And then what's our change in spring potential energy? Right. The formula is x, but if our spring is oriented vertically, we can use y instead. Okay. So this is basically like what we were talking about on the previous page. But now there's something that we know, and what we know is that y naught is the equilibrium position of the mass spring system, which means what is true at that point. What's zero? Acceleration is zero because what is zero?
Force.
Net force is zero. What forces are acting on the mass? Spring force and gravitational force, right? So what does that mean about they're equal to each other, which means mg is equal to k y naught. Does that make sense? So we can substitute. In place of mg, we can say k y naught. Okay, and we're going to do a little bit of algebra. So if we distribute, we get k y naught squared minus k y naught y final plus 1/2 k y final squared minus 1/2 k y naught squared. Yep. Then we can combine like terms. We've got a k y naught squared minus 1/2 k y naught squared, which leaves us with 1/2 k y naught squared. And does this, well, we've got a 1/2 k that we can factor out. Does this pattern look familiar? Whoops, I made my parentheses too early. What is this?
Y initial plus y final minus times y initial minus y final.
Right, I think. We can say this is k times y final minus y naught squared. I mean, it's squared, so it doesn't matter which order you subtract in. Which is just 1/2 k delta y squared. So the whole point of this is that if you are dealing with a mass on a vertical spring, we can change our zero. If we change our zero to the equilibrium position of the mass spring system, then we can just treat it as though there's only spring potential energy and ignore gravitational potential energy. Does that make sense? Because our combination of spring and gravitational worked out to be the same as if we just measured spring potential energy from this equilibrium position of the mass spring system. So that's why we make equilibrium the zero, is because if we do that, we can ignore gravity for a vertical spring, which I think is interesting, but you guys probably don't care.